About how to adelize a modular form. Okay, so here we have two terms that might not be familiar, so I'll start by defining these two terms. First of all, let's define what a modular form is. Okay, so first some notation. I'm going to let H note the upper half plane. That's the set of complex numbers such that the imaginary part of the C is positive. But this is the upper half plane. Next, I'm going to let GL2 plus of R denote the set of matrices, invertible matrices with real entries, such that the determinant is positive. And next, I'm going to define a group action. So this is going to act on the set of functions from the upper half plane to the complex numbers. If I pick a positive integer, k, well, it doesn't have to be positive, just an integer k, then if I'm getting a function from h to c, let's say f, then I can define a function f slash g, where g is an element of this group. I'm going to define it like this. Here, A, B, C, D are just the entries of G. I won't have time to explain where this comes from, but you can just check that this is a group action. It's actually a right action of GL2 plus R on this space of functions. Okay. So now I can define a modular form. A modular form of weight k and level 1 is a function from the upper half plane to the complex numbers such that the following two conditions hold. First of all, it needs to be invariant under SL2Z. So that means that f slash gamma has to be equal to f for any gamma in SL2Z. Then the second condition is that f can be written as an infinite series like this, f of z equals from sum n equals 0 to infinity of a n, which is some constant, this is some complex number, times q to the n, where q is equal to e to the 2 pi I z. So this thing is called the q expansion. If you know Fourier analysis, then this is basically also a Fourier expansion, but in modular forms they like to call it a Q expansion. Okay, that's what a modular form is. Now I'm going to give an example, which is called the modular discriminant. The modular discriminant. This is my favorite function, actually. It is defined like this. Delta of z is equal to q times the product from n equals 1 to infinity of 1 minus q to the n, all to the power of 24. The proof that this is a modular form is pretty complicated. I mean, I guess this can be verified pretty quickly. You can just expand out everything. But like this is like much harder to show. I can expand it out. It looks like this. Q minus 24 q squared plus 252 q cubed minus 1472 q4 plus 4830 minus 6048 and so on. And the nth coefficient is actually going to be denoted tau of n. Note that there's no like constant coefficient there. The reason I wrote out this many terms will be useful later because I'm going to like use these coefficients somehow. Okay, that's about it for modular forms. Oh right, there's a level 1 here. There are actually more levels, but they are like much messier. Like I can't. This definition no longer works. I need to like do some more stuff about analysis, which I don't want to do, and also I don't have time. So I'm only going to consider the level 1 case, which is easier. Part 2, the second main character of the talk is going to be Adelze. Now, this is a strange word. The Adele here does not have anything to do with Adele, the singer. The Adele actually stands for an additive ideal element. And the etymology is really weird because like the Adele is an abbreviation like this. Okay, so what is an Adele? Definition. An Adele is an infinite sequence x infinity, x2, x3, x5, and this runs through all the prime numbers, such that this x infinity is a real number, and x2 is a 2-adic number, and x3 is a 3-adic number, and so on and so forth. xp is a p-adic number. And this also has to satisfy another condition, such that all but finitely many of these xp are p-adic integers. Okay, so this is a pretty simple definition. It's at least a bit less complicated than that one over there. But I need to say some more things about these Adeles before I can continue. So first of all, mathematicians, when they work with Adeles, they like to use in lots of abuse of notation. So I'm going to also use the abuse of notation. So instead of writing x infinity comma 0 comma 0 where everything else is 0, I'm just going to write x infinity. And if I have a sequence of just r's, where r is some rational number, I'm just going to write that as r, where r is a rational number. Okay. These Adeles can be added and multiplied and subtracted term by term. So like you just do the operations on every single term independently. And the ring of Adeles, they form a ring, is denoted A. Now, you might be wondering where does infinity come from, because like there's nothing infinite here. And the reason why there's an infinity is because a lot of number theorists like to write something like R equals to infinities. Like they think real numbers are infinity-adic numbers, whatever that means. This is some weird algebraic geometry reasons. So we say that this is like the infinite part, or just the real part, and then everything else is like the finite part. So we say that an adele is finite if the infinite part is 0. So essentially, any adele can be written as a sum of like a real number, the infinite part, and like a finite part, a finite adele. Okay. All right. And the ring of finite adeles is denoted A sub F. Okay, so now I can explain what it means to adelize. Now the verb adelize means to make something adelic. The adjective adelic means relating to the adeles. In this context, to adelize means that our goal is to turn a modular form, which is a function on the upper half plane, into a function phi, which lives on GL2A. Before I can do this though, I must first explain why I am doing this, because I guess that's even more important than explaining how to do this. So why adelize? Well, I guess another question is, why do we care about modular forms at all? And I have not really explained this. And there's a lot of classical motivation that you can talk about, but I'm going to take a more modern approach. So as you might know, Fermat's last theorem was proven using modular forms. And to do this, like, Wiles need to find a connection between modular forms and something called elliptic curves. And it turns out that if you want to prove this connection, you need to do this adelization. Okay, so that's like the historical viewpoint, but I haven't really explained like why this adelization is helpful. So the reason for that is something called the philosophy of working locally, or local analysis. So the philosophy states that if you have a math problem that involves like integers or rational numbers, the way you solve it is first you solve it over the real numbers, and then you solve it over the p-adics. And then you try to piece these solutions together. And then sometimes you can do that, sometimes you can't, but it's usually helpful, at least. And then if you look at the definition of an adele, that's literally the embodiment of this philosophy, because you have like a real part and a p-adic part for every p. And then I should at least say something about like, give an example of how this could be helpful. So I'm going to use Heck theory as an example. So looking back at the modular discriminant, these coefficients have a very interesting property. If you multiply the second coefficient with the third coefficient, it turns out to equal the sixth coefficient. And then if you multiply the second coefficient with the second coefficient, and then subtract 2 to the power of 11, then you get the fourth coefficient. And these are very interesting identities. It turns out that using them, you can prove a formula, which I will write down. This is called an Euler product formula. And as you can see, it allows us to separate this thing into something that's like you can like separate like each component from each prime. So now we can look at each component separately, and then it turns out that like using the p-adics will be helpful. There's these stocky parameters and the spherical algebra and all of that. Okay, I won't go into this because we won't have time. Finally, I'm going to do the construction. So, before we actually jump into the construction, I need to introduce like one more result, which is called strong approximation. So here it goes. First, I'm going to let z hat denote the set of finite adeles such that all of these components are actually p-adic integers. So before we required that all but finitely many of them are p-adic integers. Now we require that all of them are p-adic integers. These are called the profinite integers. And so the theorem that I need, strong approximation, states the follows. If I have a matrix G, which lies in GL2A, can be written as G equals gamma times G infinity times K0, where gamma lies in GL2Q and G infinity lies in GL2 plus R, and K0 lies in GL2 of Z hat. Okay, I won't be proving this because the proof is a bit complicated, but I should at least explain what these two things mean because there's an extra layer of abuse and notation being used here. So if I have a matrix in GL2R, let's say A infinity, B infinity, C infinity, D infinity. Well, the convention is that if you have a real number, then you're supposed to use infinity to denote it. If this is an element of GL2R, you can't just take this. That's not an element of GL2A because the determinant is a real number, and real numbers are actually not like invertible. Instead, what you need to do is you need to add a identity matrix of finite adeles. And only then can you like actually treat this as a subgroup of GL2A. And then the same thing occurs with here. Like here you need to add like an identity matrix of like real numbers to it. forward. So let's F be a modular form of weight k at n level 1, but I'm just not going to say that now. Now I'm going to define, Adelize it like this. Define phi from GL to A to C as follows. Phi of G is going to be equal to F slash G infinity of I. I is just the imaginary unit, if you're confused, where G is decomposed by strong approximation. So it's gamma, G infinity, K0. So this is our adelic modular form. And, but we're not quite done yet, because strong approximation only says that such a decomposition exists. It doesn't say it's unique. So we still have to make sure that this is well defined, and this is like a bit annoying. So why is it well defined? Well, let's say I have two different decompositions, like G gamma, G infinity equal to prime G infinity prime, K0 prime. So I want to show that F slash G infinity is actually just equal to F slash G infinity prime. How do I do this? Well, first of all, I can move these two matrices to the left, so I can just like pretend they're not there. And the next step is that I can decompose this gamma into a product of something in GL2R and something in GL2AF. Like I can separate out the infinite part from the finite part. So gamma is equal to, say, gamma infinity times gamma F. Then G infinity prime is equal to gamma infinity G infinity times gamma F K0. So now this is an infinite part. This is the finite part, and this is the infinite part. So the infinite parts must be equal, and the finite parts must also be equal. So this means that G infinity prime is equal to this, and the finite part must be trivial. This is just the identity matrix. Okay, so but if I have this, and K0 is an element of GL2Z hat, so I know that gamma F must also be in GL2Z hat, which basically means that all of the entries of gamma F are profinite integers. But we also know that because of how this is defined, like everything in here, because gamma is in GL2Q, so in fact, the entries of gamma F also have to be rational numbers, like of this form. So this means that all of these entries are all p-adic integers, which means that they're actually just integers. So I can deduce that gamma is in GL2Z. And next, observe that because G infinity is in GL2 plus of R, that has positive determinant. So this has positive determinant, and this is positive determinant, and this must also have positive determinant. So this basically forces gamma to be in SL2Z. And then we're basically done, because if gamma is in SL2Z, then f slash g infinity prime is equal to f slash gamma infinity times g infinity. And then this vanishes because by assumption f is a modular form, so we get f slash k g infinity. And so we have proved that this definition is well defined. Okay, to conclude everything, I'm going to just state a property that this satisfies. Just make a small remark that if you like multiply g on the left by something in GL2Q, and on the right by something in GL2 of z hat, this should not change the output because, like, by definition, if g can be written in this form, then this can also be written in this form with the same, like, infinite part. So that's how you turn a modular form into an adelic modular form.